Okay. All right. So, as we have planned, we will spend some time on principal component analysis today. So, this topic, um, it actually falls into the realm of, you know, to the broader concept of data mining, um, data science, um, to those realms, because it is not a supervised machine learning technique, but it is a unsupervised technique that basically everybody who has data sets can use to do analysis, to analyze uh, the key information from basically any kind of numeric data sets. Okay, so because for the scope of our course, we spend the majority of time on supervised learning models, like neural network based models. We have a little bit touch into the traditional models like SVM, right? But for the unsupervised parts, we spend less time on it. So this principal component analysis, PCA, is one of them. I see myself frozen for a bit. Okay, now it's back online. Okay, so we should be able to cover this today. And the plan for next Tuesday is another topic on unsupervised learning, which is clustering algorithms. And so with these two lectures, we have that is everything we are going to cover on the supervised learning side. Okay. And let me go to the next slide. Okay. So I planned this PCA chapter because really it's very commonly used technique for either analysis or as a supplement tool for other machine learning pipelines. Okay, so it is an important step. Okay, which usually comes afterwards. You have collected data and you have cleaned up your data, and you wish to have a pre-process on the data set so that all the features get more salient or get more interpretable. Okay, so we will go through some of the mathematical details about PCA, right? But for actual applications for daily usage of this technique, we don't need to implement it from scratch. But I think it's important to understand the mathematical nature of it. Okay, so actually it doesn't go beyond the range of linear algebra. Okay, we will see that it is some of the core concepts in linear algebra that form the technique of PCA. Okay, we will need to represent the data with a matrix, and then we will basically use the term. I hope you still can recall from linear algebra courses, like eigenvectors, eigenvalues, which will be the theoretical basis for the so-called principal components. Okay, and also it's easy to implement. Everything is easy to implement with Python and the NumPy, and it's actually has some hands-on experiments that you can play with given picture data or different kinds of data sets. Okay. Okay, so let's see what it is. Okay, so it is a technique for dimension reduction or dimensionality reduction, which basically can remove some of the redundant or unwanted dimensions in your data. Because we know that a data set can have very high dimensions. A very good example is because we have already covered, we have just finished the series on language data, right? So a language data, if we think of a embedding vector for words, it is usually more than 100 dimensional, right? All those vectors, they are very high dimensions. So one of the shortcomings of high dimension data is that it's hard to visualize. It's impossible to visualize on with a human readable plot, right? Unless we can summarize, we can the word I want to use is compress. Unless we want to compress the data into fewer dimensions or into lower dimensional space. Okay, and in that process, we want to keep as much information as possible. Okay, so because the information loss when we reduce the dimensions of a high dimensional data is inevitable. But what we can do is to choose the way properly so that the most important dimensions are kept after we have reduced the dimensions. Okay, so data set like image, right, like high dimensional bioinformatics data, like word embeddings, all these high dimension data is a suitable targets for dimension reduction techniques. Okay, so the example that I show here is you can think of it as a toy data sets. Okay, so it contains several features of birds, right, including the weights, the wingspan, the length, right? So given such a data sets, there are several questions that we wish to solve. First of all, like how do we visualize it? Okay, it's still okay if we only have 3 features like a weight, wingspan, or length, because we can use a 3D plots, right? Using these 3 features as axes, right? But what if we have more features? What if we have other features like the color or the length of the say the feet, the tail, right? All those features come into this data. So it's kind of a high dimensional data, right? Which is impossible to visualize all the features all at once. Okay, and another concern that we may have is that some of these features, they are not independent, like the weights and the length and the wingspan, they are actually linearly correlated. The larger kind of birds, it's more likely to have a higher weight, right? If it's longer, right? So all those features, they are not independent. So the question is, which ones we should use as the most significant representatives for describing the data, to describing the birds in this case, right? So all these questions are important and can be solved with the technique PCA that we're gonna introduce today. Okay, so let's just follow our questions and think of the definition of what are the good dimensions that we want to keep, right? Because we have more than 3 dimensions, right? So for the purpose of either visualization or better description of data, we want to, remove some of those features and keep some features that are most important. So what are the good features or good dimensions that we want to keep? And very intuitive idea is that we want to keep the dimensions so that the data that have the remaining dimensions must have higher resolution. And it means that the data points should spread out across those dimensions as much as possible. Okay, so if we keep one dimension, right, in the most extreme case, if we only keep one dimension, for example, the length, right, and it will be bad if all the data points, they cluster into one region on that length dimension, because we cannot distinguish each data point. That is bad news, right? But what if we choose a good dimension, say wingspan, and if we can observe that all the birds, they spread, all data points, they spread out across that wingspan dimension, then it's good news, okay? Because we can distinguish each data points. We can say that the wingspan is a very significant feature that describes different kinds of birds, right? And also, if we want to keep more than one dimension, right? If we keep two dimensions, two features, then we want those two features left. They are more independent, right? We don't want redundancy, right? If we keep length and weight, maybe they are more correlated, right? So we need to develop some, automatic protocol or process to help us identify the most important dimensions or most important features that satisfy these two intuitive requirements, right? The data needs to be spread out and the features need to be independent. Okay, so that is exactly what PCA can do, okay? So PCA can help find a set of dimensions that all these dimensions are independent. So in the mathematical language, it is orthogonal, okay? And the second feature is that the results of applying the PCA analysis is that all the features left, they are ranked according to the variance of data along these features, okay? So the larger variance means that the data can spread out more along that dimension, okay? So all those features will be ranked in such a style, okay? So that we can select the top one, top two, or top three or more features as the most informative features or informative dimensions. Okay, so let's carry on to use these small data sets, bird data sets, as an example to see how actually PCA can be conducted. Okay, let me shrink the window a little bit. Okay, so so this is an extreme example because we want to reduce from two-dimensional space to one dimension, which is usually not very common in practice, but it's I think it's good for tutorial purpose. Okay, so we have 6 data points and each have 2 features, which is the weight and wingspan, right? So we use weight as the x-axis and the wingspan as the y-axis, but here we use x1 and x2, okay, not x and y. So we can plot them in the 2D space, okay? And the additional quantity we can compute is the mean values for each feature, okay? So this mu1 is the means values for all these 6 weights, okay? And also the standard deviations can be computed, okay? So these are the quantities we will need to use, okay? All right, so having the means and the standard deviations computed, here is a standard normalization process, okay? That is, we have come into this process before, right? When in designing our supervised learning models. So given any type of data sets, for all the numeric features, we want to normalize them because it'll be helpful for learning a model quickly, okay, after all the features are normalized. Okay, so after it's normalized, you can see that the data points in the plot, they shift towards the center, right? In the previous slide, all the data points, they are not centered around the 0 points, but after the normalization, it looks pretty clean and nice, right? Okay, so our goal next, okay, is to find one dimension that best describe the data. Okay, so recall that we want a dimension along which all the data points have as much variance as possible, which means along that dimension, all the data points need to spread out as much as possible, right? We don't want all the data points to be clustered within a small region, okay? So that is the standard we will use to find that one dimension, okay? So in this case, the dimension we want to reduce is just from 2 to 1, right? So basically, that dimension we want to find is a linear line, is a direction, okay? So for example, if we choose to use this candidate dimension indicated by this bluish dashed line, okay? So what we can do, so what we want to compute about the variance along this dimension is something we can first project all of our data points to that dimension, okay? So for this data point P1, right, after it's projected to that candidate dimension, we will have a projected point, right? So if we look at this projection, so the distance between this projection and the 0 points is the distance, right? That's the distance we want to record. So for each data point, we can compute such a distance, okay? This distance is important because we need to use them to calculate the total variance of data points along that candidate dimension, okay? So if we compute the sum of squares of all these projections, right, sum up the d1 square to d2 square, d3 square to until d6 square, right? Oops. Slides again. Okay, so we have a measurement of the variance of data points along that dimension. So this variance is something we want to maximize, right? The more variance means that the data are more spread out across this dimension, okay? So it becomes a optimization problem, right? We want to maximize the summation of squares of all the projections, right? So we can imagine that because this dashed line is something that we randomly draw, right? If we draw the line with a different angle, then the projections would have different values, different sum of squares, right? Right. If we like make it skew a little bit for the dimension, then the projections will be different, right? Until we find a angle or find a direction for this dimension, then hopefully along this dimension, the sum of squares for all the projections are maximized. Then this direction is the one we need. Okay, it satisfies the maximum variance requirements, right? And if we find this dimension, okay, then we will just call it our principal components, or the number one principal components, or PC1 for short. Okay, so this is how we operationally define the first principal components. Okay, and if we compute the distances for all the projections along that PC1, we will find that it has the maximum value. Okay, and for PC1, we can use a vector to represent it, because it's a line, right? It's a linear line. Then we can use a vector that indicates its directions. In this case, we use the U1, which indicates the direction it's pointing to, right? All those numbers are arbitrary, okay, decided by our data sets. So it's 0.94 and 0.34, okay, and it's a unit vector, which means the length of it is the number 1, okay. Okay, so these, if we look at the new dimensions, okay, of this unit vector, it is actually a linear combination of the normalized features x tilde and x1 tilde and x2 tilde, okay, which means the vector u1 is 94% of the normalized feature 1 plus 34% of the normalized feature 2, okay, which means we are creating a linear combination of the original features to create a the principal components one, okay. It's different from the original features, but it is a combination of the original features. So it's better than original features because along these created new PC, the sum of squares of the projections are greater than the original features. Okay, so after PC1 is found, it's easy to find PC2 because you know, one of the requirements for PCA for principal component analysis is that we want a bunch of set of features that are orthogonal to each other, right? They should be, in this case, the PC2 should be perpendicular to PC1, right? So when PC1 is found, we just draw the other feature, the other direction, which is our PC2. And if we compute the projections along the PC2, then it should be smaller than PC1, right? But it's a feature that we need to keep because it is our second principal component. Okay. Then with this PC1 and PC2 obtained, then we have basically find a new coordinates for all the data points, right? They have switched the coordinates of each data point have switched from the original features to a new to a new set of features, which is PC1 and PC2. Okay. And in this case, the unit vector for PC2 is perpendicular to U1, so it's negative 0.34 and 0.94. Okay. All right. So, and because we know that those U1s and the U2s, they are orthogonal, they are perpendicular. If we compute the dot product between them, it must be 0. Okay. And the sum of squares of PC1 is for sure to be greater than PC2. Okay. So that is a operational process. So of how we can obtain the first principal components, the second principal components for a two-dimensional data sets. Okay. If we want to reduce these 2D data sets to 1D, then PC1 is our choice. Yeah, because along that dimension, the maximum amount of variance can be achieved, and PC2 provides a much smaller principal component. Provides much smaller variance of data points. Okay, so if we rotate the new the data points to the two new vectors, PC1 and PC2, it's a different visualization. Okay, and the advantage of this new visualization is that we can better tell the most representative features or the most salient patterns along the data sets. Okay, if we compare it to the left, right? If we compare it to the left one is the original plot, right? It has wingspan and weight as two features, and we can see that the data points, they have basically similar variance along the two features, right? They vary a lot along weights and along wingspan. But if we use PC1 and PC2 to represent data, then we can see that PC1 explains much more of the variance, right? PC1 has much more variance for the new data, for the original data sets, right? Which means we have something created as a more informative feature than the original features. Okay. All right. So we haven't introduced how this can be done, right? So that is our next step of how to computationally solve this problem. Okay. So I think we already have a little clue about how to solve it, because it's we know that it's an optimization problem. We want to optimize the sum of squares of the projections. So it's kind of similar to the constraints optimization problem we had before, right? Similar to SVM, right? Similar to the other type of optimization problems. Okay, so what we need to do is to describe the target variable, which is the sum of squares, with some mathematical expression, right? And then we can use optimization softwares to optimize the targets and then obtain the input variables that optimize the targets. Okay, so let's see how we can obtain this. And because we don't know the principal components yet, we will mark it as a unknown variable u, which has two components, u1 and u2, right? That is the targets variable, right? That is the variable we want to find. So, and we will use the projection. We need to compute the projection. Okay, our data is already normalized, right? For the ith data points, it's x1 tilde and x2 tilde. So the projection between two vectors can be represented with the inner product between the two vectors, right? We have the inner product between u and x, which is this form. Okay, and we need to compute the sum of the squares of the projections, right? Which is the summation of these squares of these inner products. Okay, so if we represent it with a matrix, everything will be more clear. Okay, for example, we have the capital X tilde, which is the normalized data sets from, it has 2 rows and m columns, right? Assume we have m data points. Okay, and the sum of squares of all the data points can actually be represented by this matrix multiplication form. Okay, so this is something you can manually verify on the paper, right? If we first compute x times x multiplies with x transpose, right? The x transpose will be a m by 2 matrix, right? So with inside the parenthesis, it will result in a 2 by 2 matrix, and we know the U transpose will be a 1 by 2, and the U will be a 2 by 1. So the result will be a 1 by 1 number, which is a correct dimension. Okay. So if we represent it with this, we represent the sum of squares with this matrix multiplication form, right? Then what we want to maximize it, right? And we give it a 1 over m as a normalization term. So it becomes a very typical constraint optimization problem. Okay, and our constraint is that the u is a unit length vector. Okay, this constraint is necessary because if we don't have these constraints, then there could be infinite numbers of representations for one vector, right? We can change the size of it, right? It can be pointing to the same direction, but of different size, different magnitudes. Then we have infinite number of solutions, right? So in order to have one solution, we have to have such a constraint. Okay. All right. So let's describe the problem with the form of a optimization problem. Okay, we want to maximize this 1 over m times the sum of squares, which is this matrix multiplication form, with the constraints in the equation form. Okay, remember that we have a constraint in the equation, which is basically a good news for us, right? Because it's not an equality. If it's inequality, then we have to use the Lagrangian duality problem. But for the equation problem, we can simply solve it with the Lagrangian multiplier problem. Okay, give me a second. I will be right back. Okay, so it's a typical Lagrangian multiplication problem. It's a problem that can be solved by the Lagrangian multiplier. Okay, so if we look at the within side, the matrix, it has like two components, right? Along the diagonal regions, we have the variance of x1 and the variance of x2, right? That is a statistical variable that we are familiar with. And for the other two regions, they are the covariance between the two variables. Okay, covariance basically measures how one variable, how x2 changes with x1. Okay, how x2 will co-change with x1. Okay, that is the statistical meanings of those two different regions within that matrix multiplication results. Okay, so we call this 2x2 matrix a covariance matrix. Sometimes we can simply denote it with this sigma notation, although it doesn't mean a summation. It's just a name for a matrix. Okay, which is easier for us to write it. Okay, so in order to solve it, we will use the Lagrangian multiplier method, okay, which we introduced in the first lecture on support vector machine, right? So it means that we need to constrain something like this, which is the Lagrangian form, right? Which is our original target, right? This is our target minus the multiplier lambda times the equation constraint, right? This is our equation constraint. We will move one to the left, right? And use a lambda times it. So this Lagrangian is the one we need to take the derivatives with, okay? So the next step is to take the derivatives of this Lagrangian with respect to our unknown variable u, okay? So again, it's some trick in linear algebra. When we take the derivatives of this term with respect to u, you can think of this vector u are in a quadratic form, right? It's just like u, and u is a scalar number, okay? So if we take a derivative of it, the remaining term would be the coefficient times the variable here. And for the second term, if we take derivative of it, there will be only a lambda left. Okay. All right. So if we want to solve this next we want to solve this equation, right? We want to make derivatives 0 so that the Lagrangian can reach the maximum value, right? So by solving it, if we move the lambda times u to the right, we have such a equation, and this actually reminds of us that this equation means the u's that we want to solve is actually the eigenvectors of the matrix, of the covariance matrix. Okay, by the definition of eigenvectors, it's just this form. Okay, if given a matrix and a vector, if they satisfy that the matrix times the vector equals some constant lambda times the vector, then it means the u is the eigenvectors of the matrix. Okay, so this is knowledge from linear algebra, right? So the eigenvectors correspond to a eigenvalue, then the maximized sum of squares is corresponding eigenvalues. Okay, so let's review the eigenvector a little bit. Okay, and in linear algebra we have several ways to solve the eigenvectors and eigenvalues. Okay, and these two words are from Dutch word means my, so it actually means my vectors for a matrix. So it means that it is something as some invariable properties of a matrix. Okay. So for a square matrix A and a column vector, by the definition, if we can observe that the matrix times a vector is a constant number times vector, then we can see that we can define V as the eigenvectors, okay? Because it is a characteristic vector of A, and no matter how A changes, the directions, so the directions of V doesn't change, okay? Because A is a matrix, it means a linear transformation, okay? In this case, for these certain vector eigenvectors V's, if we multiply A times V, which means we transform transform the vectors, they don't change the directions, okay? But they only changes in magnitude, okay, but along the same direction, okay? Which means these vectors explains some of these innate properties of the matrix of the transformation, okay? Let's go into the problem of the question of how to solve the problem, okay? We will need to use something called spectrum theorem, okay? So it basically says that if we have the matrix that is symmetric, okay, then it is orthogonally diagonalizable, and it has only real value eigenvalues, okay? It means that there exist real numbers and real numbers, right? So this n is the same as the dimensions of the matrix, all right? If it's, in our case, if it's a 2x2 matrix, then we will only have two eigenvalues, okay? And they are the two sum of squares for the two PCs, okay? And also there are only n eigenvectors, okay? And they all satisfy these equations, okay? So in a more special case, if our matrix, say, is a n by n matrix, okay, then in this case, it actually it connects to our data x, right? Our x is a 2 by n, right? Which is not a square matrix, but it's okay. Then we can construct the matrix like A times A transpose, right? So the result would be an n by n matrix. Or we can switch the order. If we use A transpose times A, then the result would be an n by n matrix. And we know that they are both symmetric, okay? So what spectral theorem tells us is that the two constructed matrices, A times A transpose or A transpose times A, they have the same non-zero eigenvalues. And that's actually, it's easy to prove, okay? So say if we assume V is the non-zero eigenvectors for A transpose times A, then by the definition, we should have this equation, right? And if we multiply both sides with A, then we can have the following, right? And if we associate A with A transpose, then we would have this one. So these two are the eigenvectors as well, okay? And they have the same eigenvalue lambda, right? They have the same eigenvalues lambda. This one and this one, they have the same values, okay? So this is very useful property, okay? Because, you know, when our matrices is 2 by m and m is very big, right? And it's really a big matrix, right? if we want to solve a 500 by 500 matrix eigenvector problem, then it's a very difficult one. Okay, so the quick way is to use the A times A transpose, which results in a 2 by 2 matrix, which is a much smaller matrix. Okay, but it has the same real the same non-zero eigenvalues than the with the 500 by 500 matrix. Okay, so it makes things easier. Depends on the shape of your matrix. You can always choose the smaller size matrix. Okay, and all the other 498 eigenvalues are all zero. Okay, so for the analysis purpose, they don't mean anything. Okay, let's see what's next. In our example here, let's go through this in a complete step, right? When x, we have two features and n examples, right? And the covariance matrix is like this, x tilde times x tilde transpose, right? It is a 2 by 2 symmetric matrix, okay? Which means there are two eigenvectors and the two eigenvalues, right? Which all satisfy these two equations. And assume that lambda 1 is greater than lambda 2. And after we have solved these lambdas, the total variance in the data would be lambda 1 plus lambda 2. Okay. And which means the PC1, U1 accounts for lambda 1 over T of the total variance, while PC2 accounts the remaining percentage. Okay. So what if we have higher dimensional data, like we have more than 2 dimensional? Say we have n dimensional by n, then the eigenvalues, the covariance matrix would be of higher dimension, would be n by n matrix. Okay, so there will be n eigenvectors and eigenvalues, right? All these, but if we order them in a similar style, assume lambda 1 greater than lambda 2 greater than lambda n, right? The total variance is the summation of them. And PC1 accounts for lambda 1 over T of the total variance. Okay. So that gives us some basis for doing the dimensionality reduction. Okay. After U1 is solved and U2 is solved, in most cases, the summation of U1 and U2 can solve more than 90% of the variances in the data. Okay, and we can use U1 and U2 for the visualization purpose. Okay. So next, let's see an example using NumPy. In our case, the eigenvalues and eigenvectors can be actually quite easy to solve in NumPy. You know, NumPy provides a linear algebra module. Okay, you can import it like this. And in our case example here, we create some random, some toy data sets X that has 2 rows, right? And a simply call of this linear algebra with eigenfunctions will return. Okay, so first of all, we need to compute the covariance matrix, right? The covariance matrix is like this. It's the X times X transposed, right? So the resulting eigenvalues and eigenvectors, right, will be like this. The first lambda 1 is this value, and the lambda 2 is smaller, much smaller value, which means the lambda 1s explains the vast majority of the variance. Okay, and the 2 vectors are also included here. Okay, and what's next would be a easy task. Okay, after we have solved all the n eigenvalues and eigenvectors, right, we can select say the top k eigenvalues from U1 to UK and the top k eigenvalues, okay? And we stack all the k eigenvalues, eigenvectors, it will be an n by k matrix, okay? And that new matrix will be the basis for our dimension reduction, okay? It's a k-dimensional subspace, which means we can project the data points into this subspace with this matrix, with this multiplication, right? If we use UT transpose times X, then X will be projected to a low dimensional space. You see, the X has n dimensional, but the results, new coordinates would have k dimensions, okay? We convert the n by 1 data to a k by 1 data, okay? And we can project m examples at the same time, right? From a n by n data to a k by m data. So we have successfully reduced the n-dimensional data to a k dimension. All right. So if we, for visualization purpose, we can use k's either equals 2 or 3. Okay. And the covariance matrix of the transformed data will be something interesting to look at, to interpret with. Okay, so the y is the transformed data, and if we look at the covariance matrix of it, okay, it will be a diagonal matrix. Okay, which means all those y matrix, all those y features, they are orthogonal towards each other. They are not. They don't have interdependencies, okay? Which means they are better features than the original features, okay? And all the covariance between y's, they are 0, okay? So a covariance matrix and the shape of data, they are actually related. Say in this example, if our covariance matrix looked like this, which means the features, they only correlate with itself. There's no very small covariance, then it means the data may look like this, which means they don't have correlations. The different features don't have correlations. And if it looks like this, and it means the correlation between the x1, x2, they have significant correlations, okay? And usually for visualization purpose, we would like to see something like this, because the features, though those features are more dominant features to interpret. Okay, all right. So let's mention a little detail about better methods for computing the principal components. We use the eigen value function from NumPy for the solution, but this is not the most efficient ones. SVD, or singular value decomposition, is a more efficiently implemented method. So it's kind of a reverse of the eigen vector. So for eigenvectors, for eigenvalue methods, we need to use x times x transpose to compute the covariance matrix. But in SVD, we just decompose the x directly. It will be in such a form. What's in the middle is a rectangle diagonal matrix. Okay, it contains the singular values. Okay, and the eigenvalues is the square of those singular values. Okay, because if we use x times x transpose, we can easily get the form of sigma squares here. So for implementation, for daily practice, if we want to find the principal components, we usually use the SVD method instead of the eigenvalue method. Okay, if we summarize the procedure a little bit, the SVD, the PCA analysis consists of such steps. First, we normalize it, right? And then we compute the covariance matrix of it. And then when we obtain the eigenvectors and eigenvalues, and we can then select which small set of eigenvectors and use them to represent the data so that we can reduce the dimensions from n to k, okay? And we can interpret the principal components to see how they are constructed, like how much components, how much coefficients is assigned to each original vector and so on. So for the application of PCA, it has a so broad range of applications. First is to interpretation. In the example here, after we have done the PCA, right, we have obtained the covariance matrix, right? Then this is the singular values, okay? And then we have the lambda, lambda 2, and lambda 3. So which means the two components, they have explained more than 99% of the variance, okay? And the PC1 is 22% of length plus 41% of wingspan plus 88% of weight, which probably means characterize the size of a bird, right? And if we look at the second PC2, it is 25% of length plus 85% of wingspan minus 46% of weight. So it probably means a different meaning than size, right? Because it's a negative coefficient before the weights. Okay, so it probably describes the stoutness feature of the bird, right? So the PCA results provides new perspectives of explaining the data, of interpreting the data. And another typical application is data compression, right? And the example that we will go through in our assignments will be an example similar to the eigenface example here. So eigenface is a classical example of using PCAs, okay? So we have a data set that have m face images, and each has a dimension of 100 by 100, okay? So what we need to do is to flatten each image to a column vector, right? So that we have a data sets in 10,000 by m, right? And then we need to compute the eigenvectors and the eigenvalues for the covariance x times x transpose, right? Which is 10,000 by 10,000, right? So our each eigenvectors remained is 10,000 by 1, and we can reshape it back to 100 by 100. So the resulting phase would be like the eigenphase. But this eigenphase is really useful in recognizing new phases. Like if we have a new phase, I can project the new phase to that eigenphase, and then the projected phase can be compared with all the phases in the training sets, in the data sets, to see if it's a match. Okay, if it's not matched, then it means a new phase detected. Okay, so all those 10,000 eigenphases can be used to represent new phases. Okay, we can project a new phase image to a selected subset of those eigenphases. We don't need to use all of them, but we can maybe select the top 2, top 3, or top 5 eigenphases. Okay, so usually we will choose 100 to 150 eigenfaces. Okay, so in a classical example here, if we plot the first eigenface, it will be something like this, which don't have a detailed details about each specific face, but it's kind of a summarization of the key features of all the existing faces in the training set. Okay. Kind of scary looking, yeah. So because it's not a characteristic of one specific face, it summarizes the most typical faces of the whole data sets. So in our assignments, we're gonna change a little bit. We don't use face, but we use hands. Okay, but the same example, it's the same principle. We can use the principal components of the covariance matrix of all the hands images, and the resulting PCs are the eigen hands, right? We can use it to recognize new hands gestures. So the lecture is so far all done, and I think I can release the homework for this one later today with a Jupyter notebook, and in which you will finish the part for computing the eigenvalues, eigenvectors, and use a example of the eigenhands images, eigenhands task. Okay. Are there any questions? Okay. So if there are no questions, I will call it a class for now. And so for next Tuesday, I think I can go back to campus, and we will have our usual class meeting in the classroom, and we will discuss something about the clustering methods, clustering algorithms like k-means and other types of clustering, right? So PCA plus clustering will be the last parts of assignment work for this semester. And after we come back from Thanksgiving, we can spend 2 lectures on the generative adversarial network, which is a more advanced topic, but I think it's one of the future directions of deep learning models. Okay, so that's it for today, and thank you for coming. I can upload this video later to YouTube and post it to instructor, so you can view it later. Yeah, thank you so much.